So before we do that, it's worthwhile considering that once again, if I have at any given point, let's say this is the point x. Now if I have differently oriented surfaces, this statement says that the stress vector should change just depending on how I rotate my surface. But here you see that there is of course an uncountable infinity of different ways of rotating it just in 1D, and then you could rotate it also in the second direction and the third direction. So it seems to have a triply infinite set of possibilities and a triply infinite set of values of stresses just at one point. And this would seem to make the problem entirely intractable. However, this was the brilliance of Cauchy, where he stepped in to show that all you really need is just three different values of the stress vector that are directed on three mutually perpendicular planes at a given point in order to specify the stress vector for any arbitrary orientation. And that is how we shall go through that derivation a bit carefully, because it naturally motivates the representation of stress in terms of a stress tensor, and we shall see how that works out in a moment. All right. So to see that, the first step is to recognize what happens if we apply this momentum principle to a shrinking volume of fluid. So imagine I look at this again, this small piece as a material volume, and now I start to shrink it down around the point at its center, let's say. So what would happen? You see that these terms here, the acceleration terms and the body force terms are volume integrals. So they will be proportional to L cube if L is the mean length of this volume. So let me draw something here. This is my volume, and let's say it has characteristic dimension L. So using the mean value theorem of calculus, which basically says that I can approximate or bound the value of an integral by taking an appropriate average value of the integrand and multiplying it by the volume. This basically means that my momentum equation, for small l, that is as I start to shrink the volume of consideration, will look something like some mean value times L cube for all the body force terms, right, should be equal to some mean value times L square for the surface forces, and these would be the volume forces and the acceleration or the rate of change of momentum. So you see now that as L shrinks, clearly the left hand side, the volume terms will go to 0 faster than the right hand side because of the L cube versus the L square dependence. Therefore, for small l, that is in the limit of L tending to 0, what we would really have is the integral over the surface forces must tend to 0. This is in the limit of a shrinking material volume. So now this itself has a couple of important implications. Sorry, I forgot the limit sign here. Yes, it's better to write it this way, is equal to 0. Okay, so this has a couple of consequences. The first consequence is that it reinforces our heuristic discussion about the fact that the stress vector should have a dependence on n. Why? Because if the surface forces have to sum to 0, some portion of the surface forces must cancel some other surface forces. But however, as the volume shrinks, the dependence on x will give us only a single value. That is, basically you're shrinking around the point x, so that variations in x cannot account for different signs of the surface stress vector. Rather, it is change in the orientation n. So if my volume becomes very small around a point x, so that the value of t on this side is the same as the value of T on that side. Nevertheless, they will cancel out each other because the surface normal is oppositely directed. So this immediately implies that T depends on n. So that's a formal way of seeing this, if you had any doubts left. Okay, but now in addition to that, this idea, the fact that the surface forces must balance on a infinitesimal volume, allows us to actually represent the surface stress on an arbitrarily oriented surface in terms of just three pre-specified surface forces. And this is what Cauchy realized and used to prove his fundamental theorem, which represents the stress tensor in terms of the normal. So that's what we will do now. So consider a point x, which, let's say, lies on the surface of a material volume. And now around this point we shall construct a small tetrahedron. So first consider a plane of arbitrary orientation, right? A small triangular planar element of area which has an orientation n, completely arbitrary, and this plane is located just above the point x, and the point x lies on our actual surface of interest. Now just around this point x we will complete a tetrahedron by joining it in this fashion with three other triangles. Forgive my drawing, but oops, yes, let me do that a bit better. There we go. And so what we've done is we've enclosed this triangle by three mutually perpendicular planes which are behind the triangle, and we're going to adopt now, for simplicity, a Cartesian coordinate system, but really it can be any perpendicular coordinate system. Yes, so this is x, this is y, let's say this is z. So now these planes that we have correspond to the following normals. The normal here is nothing but minus Ez, the unit vector in the z direction. Similarly, the normal to that plane is minus Ex. Yes, and the normal to the plane behind the board here is minus Ey, and the normal to the triangle that we see on top, this triangle element, is n. All right. So now the point is that this triangle tetrahedron element that we've drawn is small, and as we shrink the volume of this element around the point x, we require that the sum of the surface forces must be 0. So assuming that we shrink down this tetrahedron, it means that basically the sum of all these surface forces must go to 0. So let me call the surface force T acting on this bottom plane, right, T1, or sorry, T3. So I'll use 1, 2 and 3 to represent XYZ, or let's just use, since we are already committed to the Cartesian notation, let's just use, let's just stick with that. So this is TZ. The TZ is the surface stress acting on the plane perpendicular to the z direction, that is the bottom of the tetrahedron. Similarly, on the surface directed in the negative Ex direction, we'll have Tx. The surface directed, surface stress directed along Ey is Ty. And finally, the stress directed on the plane of orientation n, where n is the normal, will be T. So the idea is, as the tetrahedron collapses to this point, which lies on the surface of the material volume, the required stress vector is T for the surface of orientation n, and we want to represent this T in terms of the surface stresses at the same x point, but which act on three pre-specified planes, that is the mutually orthogonal planes perpendicular to our coordinate lines x, y and z. And it is assumed that at this point we have a way of finding tx, ty, tz because the planes are pre-specified. So if we know tx, ty, tz, we should be able to find t for any given n. This is our objective here. And we can write a formula representing these by appealing to the fact that as this volume shrinks to 0, the sum of all forces should go to 0. So let's just write that down. So this statement for our construction leads to the following. It says that T times, of course, the area on which it acts. So I'm going to call that area delta A. So delta A is the area of this upward facing triangular element, which has the unit normal n. So this plus Tx times delta Ax oh, I'm sorry, I missed out a crucial point here. You see this vector Tx, which I've written as Tx, is not the surface force acting on a plane. So what is the definition of Tx? We choose Tx to be so Tx is the surface stress vector acting on a plane perpendicular to the x direction or perpendicular to Ex, right? And similarly for y and z. But now the plane that we have chosen here is not perpendicular or is not oriented along Ex, it's rather oriented along minus Ex. So this is t in the minus x direction. Similarly, this is t in the minus z direction, and this is t in the minus y direction. And what we would like to do is represent t in terms of tx, not t minus x. So we need a relation between t minus x and tx, which we shall come to in a moment. But for now, just write it down as we have it. So this is not t in y, but t minus y times the surface, the surface area of the y oriented element, and the surface stress acting along, again, the surface perpendicular to minus Ez, or oriented along minus Ez, times the delta Az. So all of this should be equal to 0. Now, how can we relate t minus x to tx? Well, this is quite simple, because from Newton's third law, right, which basically says that forces act equal and oppositely. So essentially, the force acting on this let's choose tx. So the force acting on this surface pointed in the minus ex direction is just exactly the opposite of the force that would act on the surface if I considered the element, the surface oriented in the ex direction. So this would mean that it's the force acting on from this fluid on this side onto the surface. So this just means that t minus x is equal to tx. I realize that this can be a bit confusing at first glance, but it's really just a matter of the convention of how we define t. Let me just pause here to give you a bit of an explanation that might make it easier. So just thinking about our, let's take a surface again. Let's just say that this is the unit normal n. Alright, and this is a part of a larger bounding volume. Alright, So this we could think, so if this is the surface, we could think of so this is the full surface. Now there is some material inside the surface, then there is some material outside the surface. So this is what's inside, of course, and we have some fluid outside. So the framework or the convention we've adopted here, and which is general, is that the unit normal, which defines the orientation of the surface, is defined such that it points into the outer fluid or into the outside, and therefore the stress vector T, which depends on n, is due to the forces exerted by the outer fluid on the inner fluid. So now you see that if I want to know the reverse, if I want to know the force exerted by the inner fluid on the outer fluid, I would have to find the force acting on the other normal, the minus n. Yes, I would have to know the force acting on minus n. Okay. Yes, so I would have n directed into the fluid. This is minus n, and this vector would be minus t, because from Newton's law it has to be equal and opposite. If the force exerted from the inner fluid on the outer fluid is minus t, only then the force exerted by the outer on the inner is t, and it's exerted at the same point and on the same surface essentially. So what we see from here is that quite generally T of n must be equal to minus of T of minus n, and this follows from the way in which we define n. Yes, let me just put up my vector arrows. Yes, the way we define n and Newton's third law. I hope that clarifies things a bit. Alright, so that was a brief aside. Okay, so from this we see how now that T, the stress vector acting on this plane pointing in minus Ex direction, where the normal is minus Ex. So that's what I mean by T of minus x. So the negative of that would give us the stress acting on the surface whose normal is Ex. So then by applying this to the y and z directions as well, I can rewrite this equation as T times delta A minus Tx now, delta Ax, minus Ty delta Ay minus Tz delta Az is equal to 0. So this is where we have reached so far. We reached here by using the fact that the surface forces acting on a shrinking volume must balance, and then we've constructed a volume by starting with an arbitrarily oriented planar element surface. We created a tetrahedron around that surface using three predefined mutually perpendicular planes based on our Cartesian coordinate system. We assume that we know the stresses acting on those Cartesian coordinate planes, which are basically three vectors that we have to somehow specify, which we will come to later. But the goal is, just in terms of these three vectors, we want to be able to specify the stress force on an arbitrary oriented segment, thereby reducing the uncountable infinity of unknowns for every possible orientation to just three unknowns for Tx, Ty and Tz. Okay, so the next step now, in order to get a complete formula, is to somehow relate the area delta Ax, delta Ay, delta Az to delta A. And that's simple because you see that delta A is related to delta Ax by simply being projected. So in other words, delta Ax is the projection of delta A onto the x direction. Yes, that's clear from our construction. So the surface here of this triangular element, of the biggest triangular element delta A, if I were to project it along the x direction, I would directly get the area of the triangular element that is perpendicular to the x direction. And that just means that delta AX is equal to delta A into n dotted with EX. So it's the portion of n along EX, which will be a fraction clearly, and both of these are unit vectors. So that fraction of delta A is delta AX. Similarly, delta AY is n dotted with EY. And of course, delta AZ is delta A times n dotted with EZ. Now, for simplicity, I can write, or I can represent n, the vector itself, in terms of its Cartesian coordinates, nx, ny, nz, nz, right, where of course nx is nothing but n dotted with ex, and similarly for ny and nz. So these are simply the components of the normal specified in the Cartesian coordinate system. So what all of this means now is that if I come back to this equation, making use of this machinery, we can now write, if I take delta A common and I take the tx, ty, tz to the other side, I can say t is tx times nx, where this is a vector, this is a vector, and this is the scalar component. So it's tx times nx, ty vector times the ny component plus tz vector times the nz component. But what is this? Well, this is just, so you see, I have linearly combined three mutually perpendicular vectors to get the stress vector for any arbitrarily oriented n. So I have reduced, as I had said earlier, what seemed like an uncountable infinity of possibilities of unknowns based on the infinite orientations that the surface could take. I have written that just in terms of three unknown stresses. So that's a huge simplification, and that's the genius of behind the Cauchy's theorem. But we're not done yet. We can still represent this in a neater way using ideas of matrix algebra or tensor algebra. So what we should recognize here is if I collect the components into a vector nx, ny, nz. So this is nothing but I'm writing it as a row vector, but it is basically n. Yes, and what I've written here is nothing but a matrix multiplication. If I create a matrix out of the vectors which are three component vectors tx, ty, tz. Yes, then what I've done on top is nothing but the row multiplication of the vector n with the matrix formed by the stress vectors tx, ty, tz. So what is this quantity now? This will be a 3 cross 3 matrix, and that's what we call a tensor. And we can write this tensor, we name it capital T. This is the stress tensor. The stress tensor, and this n is of course the unit normal. And so I can write finally the Cauchy's fundamental theorem to specify the stress vector for any arbitrary orientation n at a given point x. Yes, the orientation n at any given point x in terms of the stress tensor at that point x. So I'll use 2 overbars to denote a tensor. Yes, pre-dotted, right, this taking the scalar product of that tensor with the unit normal n. Yes, that's a wonderful the simply result, where the stress vector T is simply n dot the stress tensor capital T. And the spatial dependence is entirely locked into the stress tensor, and the orientation dependence comes out in the form of the dot product with the normal. Before we carry on, let's look at the form of the stress tensor once again. So where T, now remember as I said, the T has 9 components. It's a 3 cross T stress tensor, and we can understand what those components are from here. So the first component is going to be the stress oriented in the x direction, because the stress acting on the x directed surface. So all of these components are associated with stress acting along the x oriented surface. So the first subscript that I have here denotes the surface, but then it's going to act in 3 different directions, right? Because this Tx, which acts on the x surface, itself has components in the x, y and z direction because it's a vector. So this is the x component of the stress in the x direction, and this is the y component, y directed component. This is the z directed component. Similarly, I'll have the decomposition of the stress vector small ty in terms of tyx, tyy and tyz, where again tyz is the z directed stress acting on the y oriented surface, and so on. Similarly, I have now tzx, tzy and tzz. So if you look at this, so this is the stress tensor which we would have encountered earlier, but now you see how it arises out completely naturally from our derivation of the linear momentum equation. Moreover, you can understand now clearly the interpretation of these 9 components. So if I look at this matrix or this tensor row wise, each row represents the stress vector, which is a force per unit area, acting on the x directed surface, the y directed surface on the second row, the z directed or z oriented surface on the third row. On the other hand, if I look at this same tensor column wise, the first column here represents the net force acting in the x direction due to the stresses acting on all the surfaces, the x, y and the z surface, and similarly the other 2 columns. But the most important interpretation is the row wise interpretation, and n dot t is simply a combination of the rows of t with the components of n, and that's essentially what our equation that we derived here requires. Okay, so this is the Cauchy's fundamental theorem. And I hope that by going through this derivation now, you will feel some more comfort with dealing with the stress tensor, now that you see that it is actually a huge simplification of the general situation where the stress could have infinite different values based on the infinite orientations of a surface. But now we are able to decompose that seemingly intractable relationship by bringing n out and saying it's simply n dot a stress tensor, where the orientational dependence is entirely in n, and the stress tensor now is only a function of space, and it has a definite value. The 9 components of it have a different value at a given point.